Okay, so now we're going to be looking at writing functions and then pointers. So functions and pointers. So we use functions to help us stay organized, and it helps us to conceptualize a program, breaking it up into different pieces. When changes are made to a function, they can instantly take place a change from everywhere that function is called, and essentially that's why we use libraries too. So hopefully you're aware of this sort of model where we have a function name. I'll just change the color of my pen. Oh, my pointer. So we've got the function name. An example of a function would be, say, the sine function on a calculator, where you put an angle in and then you get a value out. So this is a function on a calculator that does a predefined calculation, and inside your function you give it a name, and then you put some statements that will form the body of that function, which will use these input values, or values as input, and it may not have anything to return. What do we put here when there's nothing to return? There's a word that we put there. I can't see the bottom. Yeah, void. So we've seen these in the void setup and the void loop. So if there's nothing to return, we press void. We'll see later on that when we're using pointers, and also arrays with pointers, because we're sending the array or a pointer to an array to a function, then we would not have to send anything back, because we're sending pointers, we don't need to actually return the values. So it depends on the complexity of your program. So this function name needs to be chosen carefully, and you don't want to choose a name that's already the name of a function. So these are passed to the function, and this is what's been returned, and it can be any type, any C data type. So the first example of a function is very, very basic and allows us to reuse blink code. So for example, if you want to have we've got pin 7 as an output pin, or pin mode D7 is output, void loop blink LED. So blink LED, there's no variables passed and nothing comes back. The reason is, in this case, in the function here, we got D7. There should be the void blink LED function can directly know that D7 is pin digital 7. So it's digital write D7, and it's turning it on. Turn the LED on. High is the voltage level. Delay it for 1 second. By the way, this bit has come off the previous line. It should be here, so I apologize. Then turn it off for 1 second. So that's our very simple program, but we've added a function. Have any of you written functions already? You put your hands up if you have. Yeah? Just wondering how many. I think I might add some extra questions to the second quiz. Like, have you done this? Have you done that? Because I know that I'm asking in the class, but I'm not got. I don't know how many. Okay, so one per class now has written a function. Okay, so out of the others who haven't written a function, essentially what we've got here is that in this first very simple function is a copy of what you could have in your code, but it's in a separate function. It can be placed either below or above it in the Arduino sketch, or even in another file, in another INO file. But I've placed it underneath, and I've just put a square, a rectangle around it to highlight it. Can you make functions with other than? Yes, you can. Yeah. Yep. I'm going to show some in a minute. It's just that I chose this one as the most simplest function, where we're not actually, this first one version, we're not passing anything from or to. Cool. So now what this one is this slightly the next step. So we've got this function runs, what we're doing now is we're blinking an LED. So we're saying in this case we want to specify the time. So we're saying that we want our delay time to be a value. So void blink out. This is our program now, our function now even. So this is still a void blink LED, still called blink LED, and we're passing to it an integer called delay time. It's not called delay time in the void loop. It is whatever is passed in between these brackets. Within this function, it is a local variable called delay time. If you in the void loop here, if you typed in between these, because this is the main program, in between these two brackets, if you said delay time, that variable would not exist in the void loop. Does that make sense? Delay time only exists in the function. So here we have, again, digital write D7 high, and we delay it, so we keep it on that delay time, which has been passed in through the main function, the main void loop, and then we make it low for that delay time. So delay time is only available in this rectangle. So the next one is to say, okay, we want to use the same function, but we want to blink different outputs. I'm seeing LEDs and blink the LEDs, but we want to make it high and low for different outputs. So we're now saying that we've got LED, pin D7, digital 7 and digital 5. So this time we've got LEDs on different pins. We could use our LED array, I can't remember, LED pins array from our previous program and combine and send each element of the array to the same function. if we wanted to make it a bit more complex, and delay or turn those LEDs on for different times. So in this case, we're going to call our same function. However, this time we've got two inputs. We've got int delay time and int LED. So how long do we want the blink for, and which pin are we after? So I've chosen lowercase for inside the function and uppercase for outside in the void loop, just to distinguish between the two variables. And so one, the capitals, LED 1 and 2. Yeah, I've got a question. Do you want to ask? Have you got a question? Is it Mansour or something? He's got his hand up. No. Down to the bottom of the comments. Okay, I'll assume you have. Oh, okay. Okay. So lowercase is inside the function and also delay time, and uppercase is in the main program. So this time we are going to blink LED 1 for 100 milliseconds, then repeat, and then LED 2 for 300 milliseconds, and then LED 2 for 300 milliseconds. So as you can see, we could incorporate our LED pins array that I showed you in the previous one of the previous Tinkercads, because we've opened many today. So we could incorporate that in the same program and blink those LEDs. Oh, it's not letting me. No, not on the right page. So, for example, now if we use a function in a different way, in this case, the function checks the value of an analog input. I'm going to check that it maps it to the range of 0 to 3, and I'm just going to put in there not 0 to 4, maybe. I'll check. Then returns the resultant range. It returns the value to the calling code by using the return keyword. So this time we are returning. We are going one stage further, and we are returning a value. So note that the function starts with int instead of void. So now we have, where's the int void setup here? Is it on the next page? Yeah, it's on the next page. Okay. So also that the function starts with int instead of void, which sets the type of value the function will return. So what I'm going to look here is, this is the function here. So we've got an int at the beginning, and in this case we have no inputs to our function. You can have inputs and return value. So in this case, we've got a sensor range. So int sensor value equals analog read sensor. Fact. Why does that not have, unless sensor, let me just check. Okay. Right, so this is a good example. So sensor here is declared as a global variable. What does that mean? Can it be seen in void setup? Yes, it can. Can it be seen in void loop? Yes, it can. Well, this is a global variable also. They're both globals. And can it be seen, so it can also be seen here and here. Can it be seen in the function? Yes, it can. So if it was modified in the main program, we could still see it here. So it's not had to be passed. So there's different ways of doing things. So now we are saying int sensor value, and we're reading sensor. So it's not had to be passed, but it's been declared as a global variable previously. So here the analog read already knows that sensor is referring to pin A0. So it's now doing what we previously explained. So 0 to 1023. So we've got 1023, sorry, 0, 1020. Oops, Control Z. No, I can't do Control Z yet. 1023 divided by 4, and I'm not going to do the maths. 1023 23 divided by 4, so we've got times 1 times 2 times 3 times 10. So the range is that range 0. This is going to be range 1. This is going to be range 2. And this is going to be range 3. Does that make sense? Just because I haven't done the actual maths. Can't see, but this won't loop right. What? The function won't loop? The function won't loop, however, it is in the void loop, and the function sensor range is being called from void loop, so that will loop. So we're still in the function. So we've calculated sensor value, which is a... Okay, I thought we closed the void before. No, I haven't. It's good that you've asked the question because it clarifies it. So we were still on this line here. So I was showing how we determined zeros, 1, 2, 3. And then we're returning sensor value to the main program or wherever it was called from. So we're back here. So range now has a value of 0 to 3. And we're going to print that value as range, which is very similar to the example that we did in the quiz, but without the function. Oops. And here what I've done is just, which is actually commented out for now, but done a switch of range, and you can do case 0 to case 3 just to check that you are going into each case. Now, I highly recommend using switch case in your programming, but whilst you're testing them or debugging your program, I do recommend that you put these serial prints in just to make sure that you're getting into the right case in your switch case, so you get into all of them. Once you're happy that your program is correct, I would suggest removing your print lines on serial monitor, keeping those to a minimum, because that will make your program be more efficient and go faster. I'm just going to go over to this one, I think. So this is functions. I have the code. Come on. My mouse is going a bit strange today. I won't be doing that, maybe. For some reason, my mouse is appearing and disappearing, and I don't trust it. So I'm going to go back to the PowerPoint, concentrate on the lecture, and maybe making the video separately when I'm not sharing. So I do have two, not me, these are general videos on pointers, so they're not my videos. I've just chosen two videos at random on pointers. So we'll now move on to pointers. Obviously, you will be using functions, and you'll be doing that in your laboratory for this module too, and also in your project you'll be expected to use functions. So now I'm just going to go on to, has anybody ever used pointers? We had one person in the group that had used functions before. Has anybody ever heard of pointers? Used pointers? Heard, yes, but never used them. Do you know why we would perhaps use them? There's a bit of a delay between. Don't think. Okay. So it's all in terms of saving processing power, space, improving speed, and improving performance. So rather than actually passing the variable backwards and forwards, we pass where it's stored. So whenever we have a variable, we need to store it somewhere in the stack of the device. So it allows us to pass the address, of a variable created on the stack to a function instead of creating a copy. So if we are sending lots and lots of functions backwards and forwards, that is very wasteful. So they can be used to traverse and examine areas of memory allocated in different ways. Pointers are used to manage memory in a computer programming. So if you've programmed in C, which I believe some of you have, and C++, although we've not really used pointers, they are one of the most complicated subjects for beginners in learning C. Possible to write the vast majority of Arduino sketches without ever encountering pointers. However, for manipulating arrays, pointers can really simplify the code. So things that we need to know is don't use keywords for variable or function names or Arduino function names. So you can use lowercase a to z and uppercase a to z, and you can use the underscore character. So the same as old-fashioned name filing, you can use characters 0 to 9. So these are all valid names for variable or function names. And these are invalid names. So this one's invalid because it's got this at the front. This is invalid because it's got the percentage sign at the front. This is invalid because it starts with a 4. This is not good because it's got the dash. This has got a negative. This has got the ampersand. This is at the at. And this has got a question mark. So they're not good. Valid. Good naming convention is to start with lowercase letters, and then as each word, we have an uppercase. It just makes it easy to write, to read even. So my friend, toggle printer, empty paper tray, closed drive door. And we can have Boolean data types, which are true or false. So a Boolean, my switch, equals false or true. So obviously don't use the word false or true as a variable. And store the state of the switch. So switch state equals read switch state, a particular switch. If switch state turns switch off, and we want to. So this is an example of similar to our push button. If it's changed, turn it off, otherwise turn it on. So defining a variable and declaring a variable are very different. So let's take a simple definition of an integer variable called val. So we can say int val or value. When the compiler sees this statement, the first thing it does is check the statement for errors. It'll look for 3 types of errors. Is there a syntax error? So an expression that doesn't follow the rules. So does it have a correct type? And is the variable, does it have a suitable name in terms of, does it not have those characters that are not allowed? And does it finish with a semicolon? So semantic errors they follow the rules, but they're used in the wrong context. And then there's a final one of logic errors, which are bad algorithm implementation. So there's no other errors, but it doesn't give you the desired results. So that's why we use debugging to check that our program is doing what it's supposed to. For example, declaring and defining variables. The dog meowed. So it does follow grammatical rules. However, semantic rules are broken because dogs can't meow, because cats meow. So the symbol tables, the compiler scans its symbol table to see if val has already been defined in a program. So as you know, if you define a variable twice, it doesn't like it. So this is a simplified table. So we've got a variable called myData. It's an integer, and its value is 0 currently. Its L value, I'll explain this in a minute, but this is the lower location in memory, or the starting point. X is another variable, and this is a floating point variable, and it also has a value of 0, and its L value is 610. So this shows that 2 variables have been defined. Their ID is their name, their identifier or name. So meter is an int and X is a float. And the first 3 columns are the attributes. The L value for a data item is its memory location. So where is it stored in memory? So at the moment, val it's correct. So it's been added to the table here. It's an integer and it is 0. However, it's not been placed into memory yet, so its L value is still unknown. It's not been allocated a space in memory yet. So the compiler checks to see if it's already defined. If it is, it issues an error. The memory manager is requested to find 2 bytes of, say, 2 bytes that are free. So let's assume, for instance, 625. So we're starting at 625 now. So val is defined if it has L value stored in the symbol table, which now it does. It's declared if it exists in the symbol table but has no assigned L value. So it's defined if it has an L value. It's declared if it exists here but it doesn't have an L value. So that's the difference between declared and defined. So from the previous table is the L value is what is stored in the items. So this is where it is in memory. So the L value is the starting address or location or address. The R value is the contents. So what is stored in the item's L value? At the moment, we've got a question mark in R value. Since it could be any random number, we always need to initialize it. So when we say int val equals 0, what do you think would be in R value? Yeah, I've got a real delay in seeing the comments today for some reason. Okay, so we've got a 0. However, on the next slide, we've assigned it a value of 10. So interval, after it's been defined, is 10. So the compiler will check the syntax, finds val in the table, and place 10 in binary into 2 bytes, since it is an integer at memory location 625. So at memory location 625 and 626, so 625, this is the least significant bit, this is the most significant bit, and most significant bit, it probably would be easier to put them the other way around, and the least significant bit. So here we have 2 plus 8, which gives us 10. So in 626, we are not, the point is, we are not putting any number in 626. However, because it's an integer type, we have space in 626 if val gets larger. So we've reserved that space. So we've reserved 625 and 626 for val. So most PCs store the low byte first and the high byte second at the memory locations. So that's what we've done here. So this is what it looks like. We're at start off at 625, but it's an integer value. So we know it's times 2 bytes. So another Another variable can't be stored in 626. When do you don't define the 625? It's defined. It's you can find out what it is, but you don't define it. It's the next free space. Okay. So, for example, val and letter are variables. Place them in memory at, say, 625 and 7. In fact, actually, I've just, you can actually do it. So, and 700 respectively. So, int val is 65, and char is letter. Letter equals val. So what this is here is in 625, oops, in 625 we have stored 65. So 2 bytes stored as an integer in 625 and 626. So we stored 65 in decimal as a so if this was all ones, what would the maximum be? 2 to the power of, what's 2 to the power of 4? Sorry, 2 to the power of 6, isn't it? 1, 2, 3, 4. Yeah, 16. So here we've got 65 in decimal, and that is stored in 625 and 626. We would keep adding zeros. To the 0, 1, 2, 3, 4. A second. Another comment. Wait. Yeah, that's what I'm just trying to work out. That's what I'm just trying to work out. So int val equals 65. We put in 65 in here. So let's just go to and do it in the calculator rather than MATLAB. Calculator. Like a programming calculator. Programming calculator. 65. Binary. Yeah, okay. Good. Right. So, can you see what we have here? So, a 65 is in binary 1, or the top, so 626, because they're the wrong way round. It's exchanged, yes. So the 0, 1, 0, 0 here, here, they're the MSBs. That's the higher upper byte, and this is the lower byte. or bits even, not byte, bits. Okay, so just put that back on for those of you. So up here we've got the 65 is the wrong way around. So it's the right way around, but this is how it's stored because you wrote the most. Yeah, that's right. I'm trying to say it is correct on the slide, and it is the other way around. Okay, so it's the actual answer, if we did it logically, would be 0, 1, 0, 0, 0, 0, 0, 1. So that would be 65 in decimal, and this would be 625, and this would be 626. But we're showing it this way around. So in this case, we've said letter equals val. So letter equals val, but letter is a char. For chars, we only have 1 byte rather than 2. So this would be stored as an A in hex because we would lose the rest. We would only keep the does count A hex random contents 700. So this bit is lost because this is a char, which is 1 byte, and this is 2 bytes. So this would be it would have just any content. It'd just be random. So whenever a assignment expression has a larger data type than being assigned into a smaller data type, you need to avoid having this erroneous value. What we need to do is to assign or use a cast operator. So we say an int, which is 2 bytes, and a long, which is 4 bytes. So int val and long big val. If we said this, that's not strictly correct. What we need to say is we want the solution, or val, because val is an int already. Then we use the cast to say int big val. So convert big val into an integer and then make it equal to val. In the same way, we can say the type of data pointed to is an int, and we tell it a asterisk to say that it is a pointer, and this is the name of the pointer. So the type of the data that the pointer is associated with, the asterisk shows that this is a pointer and not a normal variable, and then we've got the name of the pointer. So it's the same naming rules as C variables, and we can use any valid C name, and it's common to start the names of pointers with PTR, my quiz scores, PTR name puppy. So this is an int, and pointer temp. So it doesn't matter where the asterisk is, whether it's right after the int, if there's spaces in between, or I tend to use this one, option 3, but all 3 are valid. So data type specifiers for pointers is the most critical part of the definition. It tells the compiler that this pointer will only be used with int data types, while the syntax rules allow you to use an int pointer with different types of data. However, for example, if you use an int with double, then you can lose the decimal places. So for example, these are all valid pointer definitions: int pointer sheep count, character pointer first name, long pointer big value, float pointer meters of cloth. Each pointer is defined to point to a different type of data. So the type specifier here defines the type of data that will be used with that pointer. So this is very important. So both of these define a pointer variable: char star pointer letter, int star or asterisk pointer number. So these show that they're to be used with different data types, and the compiler sees this and places 2 definitions in the symbol table and allocates the correct amount of memory for each. So for example, when the compiler finishes processing and proceeding the preceding 2 pointer definitions, the memory might look something like this. So each pointer uses 2 bytes of storage. So pointer letter 2292 to 2293, and so to store the pointer we take 2 bytes. Int pointer number 2294 and 2293, 5 even. So before char equals 1 byte and int equals 2 bytes. The R value of a valid pointer variable is always one of 2 things: either a memory address or a null. It's not safe to use. All Arduino pointers use 2 bytes for storage, and the Arduino microcontroller boards have 3 types of memory. So they have flash memory, or where the programs are loaded, and they are non-volatile, so this memory remains when the power is removed. We have static RAM, static random SRAM, random access memory. So program variables are stored here, and the volatile memory contents are lost on power removal. Usually our variables are stored there, and our program is stored on the flash memory. So when you restart your Arduino, you can usually expect to start from the initialized values again. You've got the EEPROM, the electrical erasable program read-only memory, and this is non-volatile also. So as a program runs, they come into and go out of scope and are stored in SRAM and organized in the stack. The SRAM is less than 65K. So 2 to the 16 is the max value of max value to be stored in a 2 byte unsigned integer. So it takes 2 bytes to store a memory address for the program's data. So PCs have gigabytes of memory, hence they use 4 byte memory addresses. Microprocessors are very small, so they only use 2 bytes instead to save the memory. So the char pointer is designed with a scalar of 1 byte and enabling it to see a character type. So here we have 1 byte char. The scalar value for a specific pointer is equal to the pointer number of bytes required to store that data type in memory. So the scalar of 2, we've got 2 bytes, and that's an integer. But the pointer always requires 2 bytes regardless. So the int data type requires 2 bytes of storage. This means that the int pointer has a scalar of 2 bytes so that it can see an int data type correctly. Long type specifier, its scalar would be 4 bytes. So it would be 4 bytes, sorry, another 2 bytes. So it would be for long. And a char would just be 1 is for a char. But the pointers are always 2 bytes. So after defining a pointer, it's still not usable, so we can't do anything here until after the compiler processes it. Have an int pointer that has nothing in it, or a garbage R value. So suppose the compiler ends up placing the pointer at a memory address of 2294. That could have a value in it from a previous program, or it could have a null in it. So what we need to do is we need to set the R value. Sorry, if we don't initialize it, the R value is whatever is already in there. And we are just about, we've got 2 minutes. So consider int A, int B equals 5 and A equals B. So if we go to B's L value and make a copy, the R value you find there is 5. So this is stored in memory somewhere, and this is stored in memory somewhere. So when you compile this program, so now you need to find out where is what's the L value of A. So you need to go to the L value of A and copy the R value of B into the R value of A. So A will now equal 5. Simply stated, most non-pointer assignment statements simply copy the R value of one variable into the R value of another variable, but this isn't the same for pointers. The pointer holds valid memory address or a null R variables, or a null. R variables don't hold normal variables. So consider this value. Int number equals 5. Int star pointer number. Assume number has an L value 2292. So in there we would store control. In here we would store 5. We have initialized number with an R value of 5. But we didn't initialize the pointer number. So at this moment in time, it contains, we don't know what it contains at this point in the program because we've not initialized it. We've not said equals, or we've not pointed it. Sorry, that's my window cleaner. We've not pointed it to this variable. So an and would tell the compiler, don't do the standard R to R value assignment in this statement. Instead, take the address or L value of number, so 2292, and copy it to the R value of pointer number. So our pointer, it is a pointer, But if we say pointer number equals and number, then pointer number will be inside pointer number, we will store 2292. So now pointer number is located with an L value in the memory at 2294, but it points, this is its R value, it points to 2292, and that's gone off the page, but that is the R value of, it's going a bit crazy, 5. I'm going to make another a short video of pointers, and I will add that to YouTube because I realise I am going over and you do have another class. Okay, so I'm going to add some more a place on the quiz for you to ask some questions. So please do that quiz, either the first quiz if you haven't done it, and I will be adding, in fact, there is another quiz already, a link to the other quiz in Moodle. So I won't see you next week. You'll be doing a practical, but I will be adding some videos for you to look at as in explaining this even further, because we've almost got to the end of pointers, but I was hoping to get to the end today. Okay, any final questions? Thank you. No, my pleasure. Thank you. I'm going to stop.